this is 0 to 15. This is 31 to 26, 25 to 21, 20 to 16. Okay, does this make sense for I type? Yeah? Okay, so can you guys tell me what is load instruction? Is load instruction an I type or R type? Load word? Is it I type or R type? I type. Okay, cool. That's correct. Okay. Say for example, okay, let's write opcode for load instruction. Okay. So load instruction, what should be the opcode? It's over there. 35? Yeah, okay. 35 is basically 100011. Okay? So say for example, in your assembly language, how would you write? Say for example, if I say load word $4, $5, and then 200. So, or say 20. Okay. So what would happen in this case? Come on guys, what should happen here? This is RS, RT. Come on, this is the basics of 112. Come on guys.
Does $5 have the address?
Uh-huh.
And then 20 is the jump amount or something?
That's correct.
And then it stores
$5 or $4?
It stores it in $4.
Are you sure? Isn't it the other way? It's RS, okay? So data of RS plus 20 goes to data of RT. Okay? Got it? Say for example, if your register file, okay, say for example, this is a register file. Okay? So your register file has all the values. 0, 1, 2, 3, 4, 5, 6. Okay, so 4 has like some value 30. Okay, so what happens is 30 is added to 20, and then the answer, which is 50, is stored here. Okay, does it make sense? Yes? Okay? Yeah. Cool. So now we have done that. So now if say for example, if I give you like add $4, $5, say for example, if I say So what would this do? What would this instruction do? Is this an R type or an I type instruction? R type. Okay, so what would that do?
Take 5 and 6 and add it and put it in 4. Add them together and put it in 4.
This is source, this is temporary, this is destination.
I thought it always worked right to left. Yeah.
Right or left? Are you sure?
Right. When we did this, it was always right to left.
Oh, okay.
Yeah.
Yeah.
Yeah, I think 4 is destination.
Cool. Okay. So this is destination, this is source.
Yeah.
Okay. So 5 plus 6, data of 5 plus data of 6 goes to 4. Correct? Okay. Cool. That makes sense. Okay. So say for example, if I give you this instruction, okay, so can you guys tell me the 32-bit opcode? I mean the instruction? Okay, 6 zeros.
And then what's in 6?
Do you write what's in 6 or do you?
The address.
Yes, so the address is 6, right?
Yeah.
So you just write 6.
And then 5.
5,
And then 4.
4. Okay.
And was that 4 zeros for shifting?
And then shift amount is 5 zeros.
5 zeros.
And then what's the function? The function is in your description. Sorry?
4.
4? It's a 6-bit value? Is it 4?
For destination, right?
No, the destination is done. So RS is done, RT is done, destination is done, even the shift is done. So the function, I'm talking about the function, the last 6 bits. So what's the function? No, opcode is zeros. That makes sense. Is the function 0?
Is that what's in the book?
1.
1 5 followed by 5 zeros. Okay, so you guys open your try and open your assignment description. So function is basically you need the function for the ALU. Okay, the ALU for the ALU function is 1 0 0 0 0 0. Okay, so this is the functionality. So when I give you this, then this is basically addition. Okay, this should be your 32-bit instruction set. Okay, does that make sense? Okay. Yeah.
You have the RT and RS switch. RT is on the very right.
Oh, this one?
Yeah.
Okay, that really doesn't matter. So, okay, yeah, I mean, like we okay, that's fair enough. But like ideally, like for your VHDL point of view, you should know only this. This should be good enough. Okay, so
Okay.
here if it RS, RT, and RD. Okay, so this is very important. Okay. So cool. Okay, next what I'll do is, since you guys are familiar with this, I'll try and draw a very comprehensive diagram of the complete processor, okay, and make sure you guys understand like all the signals where it goes, okay. Okay, let me save some space.
Separate reports.
No, you do this on report latex, it needs that file. So when you do a snapshot, you put it in the same folder where your latex file is. When you write your latex file, you're gonna call that file so that it just like automatically just magically appears in your latex file. That's how, like, if you looked at mine, that's how mine worked. It was just like that. It was like this. See? That's why if like there's code, when I write the code, it's something like this. You need the name of this file, and then you need the name of this file. It's kind of just like that. You just do cadence. This is what I do, by the way. I just wrote it, just cause. From your local, for remote to local, it's, yeah, SCP on terminal. Don't log into an Malibu or whatever. You first navigate to your directory, not SSH, navigate to your directory, and then once you're in that directory, do the SCR, SCP-R space, whatever. All of that, like the actual name of it. It's in the SSH client.
So you
If you open that.
don't have to log in?
No. Because it asks you for your password later. Technically logging in every time. You can even copy entire folders. You can even like copy an entire folder into it, upload it onto the server. That's what I should have done. I did it one by one. It's in the Unix thing. It's in the PDF. Yeah, it's after the colon. It's after the colon. You type your username, like mine would be aozong@malibu.uci.edu, colon, and then that's it. But if you don't put anything after it, it'll put in your home directory. If you want to specify a specific folder, you do tilde. You do the colon, tilde, slash, wherever. Yeah, that's where you save it. there's a template in the folder, the latex template. Use that one. Should use that one.
Is it colored?
So, this is really ugly. She is programmed right. Like this is all fucked up. But you don't have to worry about this right now. It's too complicated. Just wherever it is, just fill in the blanks.
That's why I said so easy. Just fill in.
Yeah, just fill in, like, replace it. Yeah, not now.
You can open up the doc text in here. You don't even need to complicate. This is just like, okay, imagine a shared Python file, right? And then you're just editing it.
Yeah, it's like that.
The latex
It's like
is like that.
HTML. Even if like, still, like, most of it will still, like, work. And usual. Just sometimes. So just edit it.
Just like, imagine this is Python and you're editing it, and then once you save, and then you run it basically latex. And then once you run it,
See, this is what I have. What you're probably curious about is right here. I made it a lot nicer. Like, this is the title. This just means caps lock and stuff. This just means bold. And the slash just means like new line. Just no, you know what I'm saying? Just new line. Yeah, the author is just this, and I made it just look pretty. I took out my team. Well, I have another template for that, but this is just mine. This is just the very beginning. This is the title, and the bulk of it is down here. See, after this, you see after this, I put a table con. You don't have to. I did a new page. Right here, it's like section. Once you start typing section, this is what you see. This is all the shit you see right here. Right? There's all this, and then see this thing. This is what I talked about. It's called my my image. That's how it outputs this. And then the second section. See, second section. This. It's this.
Okay, cool. So this is the control and data part of the processor. Okay. So for this assignment, you need to design the whole thing. Okay. So if you have done your EX31L, you should already know your register file. You should already know your ALU. Okay. So there's a difference between the previous ALU and this ALU, and I'll go through that today. Okay. You should know how the controller works basically, but there's like a little bit of difference how it works. Okay. I'll explain the operation of this controller too. And then you should know how the instruction memory works. You should know what program counter does, and then the basic add-on and stuff. And then you should know what sign extender does and stuff like that. Okay. So do you guys know what all these blocks do, or do you have no clue? Okay. So mostly, yeah, no. Okay.
That's not complete, right? It's missing.
This is missing branch instruction. So that's why these branch out, jump out, and this branch is like it's connected to nowhere. Okay. In your week 3, you'll add some more blocks, and then you connect these outputs to those blocks, and finally you make a branch instruction. Okay.
What about data hazards?
You'll do that later. Okay. So your data hazards, everything, those things comes during pipelining. Okay. So data hazards don't come like during single cycle processor. Data hazards only come during like all these hazards and.
Oh, this is a single cycle.
This is single cycle. Yeah.
Okay.
So you have to do a single cycle processor. Okay. So you're not doing any pipelining right now, so you don't need to worry about those stuff. Okay. Just a single cycle. Alright. So. Okay. Say for example, okay, we have. Okay, so let me explain block by block, okay? So the first block is program counter, okay? So what's a program counter? What does it do?
The instruction.
Keeps track of
Yeah, keeps track of
Current instruction.
you are in your instruction.
current instruction, right? So basically, okay, so, okay, you guys are like talking very high level, okay? So now you need to come to the hardware level, okay? So it's like, what does this do? So what are the so basically you need to tell me like what's the output and what's the input, okay? You have to come to complete low level. So you're talking in like bits right now, okay? So what's the output? So if input is 0, 0, 0, what's the output?
32 bits at address 0, 0, 0.
Yeah. So what program counter does is like the address goes to the instruction memory, and then the next cycle this will increment and then come back here. Okay. So ideally the whole thing, this whole section is the program counter. Okay. So what program counter does is it basically adds 0. So instruction memory contains all the instructions. Say for example you have like 10 instructions. Okay. So all the 10 instructions will be stored in instruction memory. And then program counter does, what it does is it slowly, every clock cycle, it changes the read address from 0 to 1 to 3 to 4 to all the way up to 10. And every clock cycle, a new data the instruction will go through the register block and the whole operation will happen in the processor. So every clock, since it's a single cycle processor, one clock cycle will implement one instruction. Okay, does it make sense? Yeah? Okay. So what is instruction memory? How would you code instruction memory? Okay, let me put it that way.
Is word addressable, right?
Sorry?
Is it word addressable?
It is word addressable, yeah. You can have word addressable, yeah. So you guys tell me what's the entity of the instruction memory, which Puri already gave you. Okay, and then like we'll discuss like how to code instruction memory. So it has, what is the input and what is the output? How many inputs do you have? How many outputs do you have?
One in and one in out.
One in and one in out. So what's input?
Address.
Address, which is input. So in, which is 31 down to 0, right?
Yep.
Okay, so you need to remember address is 32 bits. Okay, it's the key concept here. Okay, so it's very important. You need to understand your address is 32 bits. But obviously, so if say for example, if the address is 32 bits, what's the width of the memory? It's 2 power 32 minus 1, right? Yeah? There's a width of the memory, okay? So what's this? In general human terms, what's this called? What's this?
2 gigabytes.
I think it's 4 gigabytes. Okay? Have you ever seen a processor with the 4 gig registers? No? Impossible, right? So does this make sense? Address being 32 bits? Does it make sense? Yes? No? No, right? So address being 32 bits doesn't make sense. So what you need to do is, you need to define your instruction memory. Okay? So you can define as like, 256 bits or like 512 bits, okay? Say for example, if it's 256 bits, how many bits of address do you need? 2 power dash is 256. 1, 2, 3, 4, 5, 6, 7, 8, 8, 9. Come on, guys. 2 power 10 is 1024. Okay. So 2 power 9 is 512. 2 power 8 is 56. Yeah, that's what I'm asking. So 2 power 8. Okay. So what you need to do is you need to use just the 7 bits. Okay, of the addresses. You can define however you want. You can define 9 bits or 8 bits. Okay. Or even 10 bits, okay? The thing is, if you define 32 bits, your code won't work. I mean, the servers are not capable of running such high memory blocks, okay? So for your instruction memory, you can have this as 8 bits, okay? So you define your like address width as 8 bits, and then when you define your memory block, you can define as like, so if you define your address, so how would you define your address bits? You have like parameters, right? So what would you do in VHDL? How did you define it? There's a keyword. You guys remember it? you guys used in 31? Okay, let me give you a cue. It starts with the G.
Generate.
No, it's not generate. E. N. E. R. I. C.
Generic.
Generic. Do you guys remember generic? So yeah, you define a generic value, okay? So you define like address width. So something generic. Address width as say for example 8. You can define 7 or 8, okay? So 8 is probably a really good idea, okay? 8 is good. So when you define generic address 8, and then when you define your, your 2-bit array, so you can define as, 0 to 2 power 8 minus 1, and then this is 32. Okay? Does that make sense? So this is a good way to define your instruction memory. Okay? Alright, so do you guys remember how to define a 2-dimensional array in VHDL? Do you guys remember something called subtype and type? Yeah? Okay. Can you tell me okay, can you guys tell me how I would define
Oh, yeah.
this 2-dimensional array? You can, Google all the way. You can just go search, let me know.
You have to do slash begin verbatim slash end verbatim.
Yeah, but there's something before that. Okay, go ahead, Google and tell me, okay? So this is, here we're learning, this is a process, okay? So let me, just tell me.
Yeah, it's up to you.
Of what? So you need to define a subtype, right?
Understand how.
So first, we'll define a subtype of standard logic vector, and then we'll define a type of array. Okay, so how would you define a subtype and a type?
End verbatim. The same thing.
So I just type whatever inside.
So we'll have subtype.
That's pretty much it.
Okay, subtype of what? Don't you have to give a name? Yeah? Yeah, we could call it like, some reg type. Okay? Of what? Okay, standard logic vector. 31 down to 0. Okay. Now, since you have defined a subtype, then you need to define a type. So what's it called? How do you define a type? Type? You can give a name, right? So let's have like memory type. Okay. So this can be whatever you want. You can define whatever you want. Okay. Memory type of array. What to what? Okay, so 0 to, so we defined address width, right? 2 power address width minus 1. Okay, of what? Reg type, correct. Okay, can I define 2 power something in VHDL? Yeah? Can I define that? How do I do that? What's the operation to define powers? Come on. Go ahead. Google, search. VHDL operators, power. Star, yeah. 2 star. Okay, so 0 to 2 star address width minus 1 of rich type. So when you define something like this, the type of mem type is an array. Okay, it's a 2-dimensional array of 32 bits with 256 depth. Okay. So now if I need to define a memory one, okay, say for example I've defined like memory 1. So memory 1 is of what type? Mem type, right? Right. So can I define a signal? Signal memory 1 is mem type. Okay, so when I define memory 1 as mem type, so mem1 is basically my two-dimension array. So 31 down to 0 and then 0 to 255. Okay, so this is my instruction memory. Correct? So this is how you define your two-dimension array using subtype and type. Okay. So the thing is, over here, my instruction memory doesn't have clocks, it doesn't have resets, it doesn't have anything, okay? If you get the address, you send the data. You don't care about clocks, you don't care about resets, okay? That's very important to understand here. Got it? So say for example, when you're defining, say for example, you want to access, so I want to access, memory location 10. Okay, so how would I access? So this is my data out. Okay, so how would I access my memory location 10 with respect to VHDL code? Can I write like data out is less than equal to mem1 of 10? Does that make sense? Does this logic make sense? Yeah? Forget about the syntax, don't worry about the syntax. Does this logic make sense? Yeah? Okay, so what I'm doing is, I'm accessing 10th location and then I'm sending the data to data out. Data out is my output of my instruction, okay? So, but 10 is not the right value, so I need to give in terms of address, right? Correct? So since I'm accessing only my 8 width, okay, so I'll give like address of 7 down to 0. Does that make sense? So 10 is basically 1010, right? So location 10 is like 0000 1010. This is my 10 in decimal. Okay, so say this is my address, this is my first 8 bits of address, and then I have like all don't care terms. I don't care all this, I just take only the 8 bits here. Okay, so this is my address. So this is like 32 bits, so basically don't care of all the values except these 8 bits at the very end. Okay, that's what I'm doing. But with this, so the thing is, over here I've defined array as 0 to 2 power address bit minus 1, correct? So 2 power address bit minus 1, this is an integer, right? Correct? It's not a standard logic vector, it's an integer, correct? So can I use standard logic vector while accessing my value? No, I can't use it. I need to convert to integer, correct? So you need to convert this to integer and then like use that. So do you guys remember the data type conversions and stuff from last year?
You have to import something, right?
Yeah, you just need to define like a numeric library at the top. Instead of 1164, and then you need to define numeric, and then you can use all these. Okay, so you need to use data type conversions to make sure you convert from standard logic vector to integer and then access that memory. Okay, got it? Is that clear for you guys? Okay, cool. So basically this is just the instruction memory, okay? So do you guys have any doubts in instruction memory? No? Yeah.
Why is it just 31 bits if you only can at the bottom?
Okay, so the thing is, for load and save instructions, the thing is you have to give like, data, immediate values and stuff like that. So you need to add the values. So it's like to add the values, like the input is 32 bits. The immediate value is 32 bits, okay? So you can't add like 8 bits and 32 bits. You need to like make sure both are same. So what you do is you add it and then just take the final 8 bits. Okay. The thing is, this can be generic. You can use 8 bits, 9 bits, 10 bits, whatever you want. Okay. For this project, you can use 8 bits. Say for example, if for the next project, if Puriya says, okay, use 512, then just change this to 9 and then the whole code will work. Okay. So it's actually, I think if you see the assignment, the data memory should be 512. Okay, you can have this as 512 too. Okay, to be consistent, to keep it consistent, you can have this as 512. So you can have it 9. Okay, it really doesn't matter. Okay, so if you go through your assignment, if you go all the way down where Puriya gives like the entity of your data memory, he says like make sure data memory is 512 depth. Okay, 512 deep. So 512 is 2 power 9. So data memory is 512. To keep it consistent, you can have your instruction memory as 512 too. Okay. So instruction memory is one of the easiest blocks to code because it doesn't have any clocks and no resets. It's like just define your 2-bit, 2-dimensional memory and then like access it. That's all. Okay. Okay. My question is, do you guys use process here? Do you have to use process? Okay. Do you remember what process is? Yes. No?
You gotta watch some YouTube videos.
Okay, process is basically a sequential statements. Okay, so if you want to use any sequential statements, you need to use process. Okay, right? So here, do you think you need to use process or no?
Don't they have to execute in sequence?
Yes. So you need to have process. Correct. So it's basically a sequence. The sequence is very simple here. Sequence is wait for change of read address. Once the read address changes, then send the data. So this is a sequence. Okay, there's just like one sequence here. So this sequence you have to do it in a process. So in your process, you have do you remember what sensitivity list of a process is? So you had like remember you had process, and then you had something in parentheses, and then you begin, and then you have something right, and then you end. So this is called a sensitivity list. Okay. So in a sensitivity list, you need to have the address R, ADDR. Okay. So whenever address changes, you need to send the data. Okay. Does it make sense? Okay. So that is instruction memory. Cool. Can I erase this? Yeah? Okay.
So this week, are we building all these components?
Yes, you're building the whole thing. 2 weeks. You have 2 weeks, by the way.
2 weeks.
Yes, you need to build everything.
I have multiple types of studying one, so.
Yeah, you should have registered file from X31 too. You can, if you want. The registered file from X31 and for this is basically the same thing. Okay, including the entity. So if you have X31 registered file, you can reuse it.
Yeah, I also have to register this file.
Yeah.
I think I have data memory too.
I don't think you can use the data memory. Data memory is different over here.
Yeah, does MIPS have like a comparison?
Sorry?
Does MIPS have a comparison built into the ALU?
Yes, but you're not doing comparator here for this project. You're skipping. So MIPS basically has like
The full MIPS I thought had like a lot.
a lot. Okay, so you're doing a subset of operations. You're not doing all operations. Okay, so if you want to do all operations, you'll probably need like 1 year to do it because it takes a lot of time. So you're just doing a subset of operations, which you can like do it in 3 months. So this is what you need to know. Okay. All right. So instruction memory is done. Okay. So, do you guys remember register file? Yes? No? Okay. So, register file is basically, it has, can you guys tell me the entity of the register file given in the problem statement?
The definition, you mean it's reports?
Yeah.
I'll have one, and Sammy has a read for it.
Can you look it up?
It
It's in
has
the,
the clock,
Uh-huh.
reset, write enable,
uh-huh.
read address 1, read address 2, write address, read data 1, read data 2, and write data 1.
Right? Okay, so say for example, let me write a
What do you have problems?
class. Oh.
I got that too. What was it? Let me check.
Yeah, I don't think it's signed in.
But this isn't here. Once I know that I just have to get like this, but
Yeah, mine was
related.
I haven't saw like 10 additional tags.
Use zoom up. Make sure you're not on just the code. Make sure you zoom up. The first one.
One Malibu.
No, Malibu is Solaris servers. It doesn't have that command.
It's good for Quest, right?
Quest.
Quest here.
You can try Crystal. Maybe Crystal works. But Zuma works 100%.
Is it Malibu or
Oh, wait. Malibu is for Solaris, which is for Cadence, yeah. You did these steps, right? Yeah, Morrison is just like directed. Make sure you do source. Yeah, make sure you do. Make sure you go into that folder on the server, and then you do source and source and.
Yeah,
one
when
by.
I did source setup, I had no problems. But then when I moved to source,
Yeah, it doesn't have vcon. It doesn't have vcon built in.
how does NCHDF do? So you compile NCHDF.
You know, the instructions for that is just
copy paste?
yeah, just copy paste it.
From the cadence.
Yeah. Well, from that for Quest is to copy SCP. Wait, no. No, that's different. Yeah, each one has different commands, and not the same.
For some reason, I damaged that one.
So you can connect to the sun service.
Yeah, for some reason, I mean,
What's on the sun service? Do you have like a .x like file, like on access already?
no.
It's not there.
It's so yeah, solar.
I think it's on the main server.
I mean, yeah, it works because you still have to batch it.
Yeah, because all Unix space, Oracle owns Sun, which did Solaris. So Solaris is Unix space, Mac OS is Unix based, Linux is Unix based.
So I
All
don't
these
know, I
kind of
can't log in.
Okay, guys. All right. So this is the register file. Okay. Okay. So for this example, let's assume my register file is 8 bits wide. Okay. So this is my clock cycle. This is my reset. These are my readers. So these are all inputs. Okay. So all these are inputs, and these are outputs. Right? So this is my internal register file. Yeah.
We pretty much did this on the final project for 31L, right?
Yes, you did that. Yeah. Yeah, but like there are a couple people who are not familiar with this. So I'm just explaining.
But a lot of it can be reused.
Yes, you can actually reuse this. You can reuse the muxes. You can reuse your program counter. Okay. And then controller, you need to recode the whole thing. Okay. The controller is pretty much completely different. And so is the ALU. ALU also is completely different. You need to recode the whole ALU. And you need to recode the data memory and your instruction memory. Sign extender you can reuse. Okay. So you can reuse reg file, sign extender, and your muxes basically, and your program counter. Okay. Nothing else. Everything else you have to recode it. Okay. So this is your reg file. Okay. So you guys are familiar with reg file, right? Yeah. Okay, guys. So can you tell me what's the art? So what happens at this clock cycle? So what happens here? Oh, I have right enable. Sorry, hold on. So right enable is. Okay. So what happens? My RData 1 and RData 2 over here. Okay, can you guys tell me? So on this positive edge, this is my register file.
You looking at? No, I already took that 66.
Yeah.
Do you still know? Figure it out.
What's my RData 1? Is my write enable 0? So if my write enable is 0, what's it is? Read or write? Uh-huh. Read, right? Okay, so it's read at this positive clock cycle is reset 0 or 1? Reset is 0. Correct? So when reset is 0 and write enable is 0, it's read operation. Correct? So I have to, my read data 1 and read data 2 should be the data of read address 1, read address 2. Correct? So the value of 2 is 44, the value of 3 is 31. Correct? So my read data 1 changes to 44. Okay? And my read data 2 changes to 31.
Yeah.
Does that make sense? Okay? So the next positive clock cycle, what happens? Just reset, yeah. So reset is high. So my data will basically become 0. Right? So what happens to my memory during reset? Everything will become 0, right? So this will be 0. So the whole thing will reset to 0, all the memory locations. Okay? So during reset, everything is made to 0. Okay? So the next clock cycle is over here. So what happens here?
So right.
So what happens here?
Right enable.
Okay, right enable is high. So what should happen first? Will it read during right enable is equal to high?
It doesn't read, right?
No, it has to read. Okay?
Oh, read that, right?
Yes, it reads and writes. Whereas if right enable is 0, then it just reads, it doesn't write. Whereas right enable is 1, it has to read and write. Okay, that's the operation of a register file. Okay, so this is very important concept. Okay, you need to understand that. So when this is high, it has to basically first it has to read and then it has to write. So read comes first, write comes next. Okay, so while coding, if you'll have your like lot of if-else statements, in your if-else statements you'll have read operations, and the very end you'll have the write operation. Okay, so what happens to read data 1 here? Does it say it's basically reading from register 5 and register 7, right? So 5 and 7 are 0 zeros, correct? So there will be 0 all the way. Does it make sense? Yeah? So over here, since write enable is high, my value, so my write address is 0 and my write data is 32. So what will happen? So this changes to 32. Correct? First it reads 0 zeros from 5 and from 5 and 7, and then my 0 register is changed to 32. Okay? So the next positive edge of the clock cycle, it's reading 6 and 6. Okay? So 6 is 0 0. So this will be 0 all again. Okay? Whereas over here 36 will be written into 1. So this will be changed to 36. Okay? Next clock cycle, here read address 2 is 0, read address 1 is 7. Okay? So read address 1 is read data 1, so 7 is basically 0, remains 0, whereas it's reading from read address 2, okay, which is 0 here. So it has to read 32. My read data should be 32. Does that make sense? Yeah? Next positive edge of the clock cycle, my read data 1 will change to 32. Okay, my read data 2 will change to 36. Okay, so what will happen here during the write? 2 will become 22, right? And the next thing, 3 will become 56. Okay? So I'm just reading and writing at the same time. Finally, this is read data 1 is 22, this is also 22, and then 78 will be written here. Okay? Does it make sense? Yeah? This is basically a register file. So your register file will have like, bunch of case statements and if-else statements, and then like you need to look for priorities, and then the priority is read first and then write. Okay, that's the main thing. Okay, so what does sign extender does? What does sign extender do?
It appends zeros. Not appends, but
Appends what?
it prepends zeros to it, right?
Zeros? Is it
Just
zero?
the beginning of the number.
Say that again.
Oh, the leading bit.
Yes, the MSB. Okay, yeah, you're right. Yes, that's correct. So it basically takes the MSB and then appends it 15 times, 16 times. Okay, this sign extender converts from 16 to 32 bits. Okay? Can I erase this? Yeah? Okay.
How I did it was this. So since you have latex file, you can just do PDF latex. And then do PDF.
Okay. Do you guys want me to explain sign extender? It's good, right? Sign extender is super easy. Okay, cool. Okay. Coming to the ALU. This is probably a bit confusing, okay? Can you guys tell me the functionality of the ALU? Can you look through your project description and tell me? So the function is 1, 0. And then okay, so what are these two operations? Add. Okay, so your ALU is basically your, say for example, can you guys tell me the entity of the ALU? What does it look like? What is this? Can you tell me the names? Is AN, BN, this is function in, right? And then what's this called? Out, what? Just out? Oh, out, okay. And then B out, J out. Is that right? Just B out and J out? Am I missing anything? No? Okay. So how many bits is AN? 32. 32. Functionality is 6. B out is how many bits? 1. J out is 1. O out is 32. Cool. Okay. So okay. So your ALU is basically a case statement of all these functions. That's all, nothing else. Okay. So you can you can look through your ALU of your assignment 1 and then use that as reference and then code a different ALU. Okay. That would be like the way if the case statement is probably the slower version of the ALU, but if you want to code it like a very fast version, then you could have like look for similarities between the opcodes and then code it. Okay, so that's probably a really good way to code it, but like it's completely up to you. You can code however you want. Okay, so the case statement is basically the most easiest thing, but it's also the slowest version. Okay. So if you like at the end of the day, at the end of the project, when Puriya looks for all the timing of your project, if you coded the ALU in a case statement, then it would be probably one of the slowest projects. Okay, so yeah, I'm just letting you know. Okay, so this is add. So output would be A plus B, right? Correct? Over here, the output would be A minus B. Okay? So this is, so what are these operations?
And or
Logical. So and
or
or XOR NOR. Okay. Do you guys know why we're using NOR? Why aren't we using NOT or something? Do you know why we're using NOR?
Non-zero.
Huh?
A non-zero reference to not.
Sorry, say it again. I didn't get you. I'm sorry.
You don't need not because you cannot have register that has zero values.
Registered for zero values. Isn't NOR and NAND gates are universal gates? You know, right? So you can have NOR gates and NAND gates, and then you can code whatever gates you want. Okay, that's the reason we are using NOR gates. Okay, got it? Does that make sense? Okay. So what are the next two functions?
Load and store.
Sorry?
Oh, is this supposed to be on the assignment sheet?
Yes.
that less than
So set less than.
sign that.
This is. Unsigned. And okay, let's come to the branch instructions later. Okay. So here, your B out and J out are basically zeros for all arithmetic and logical operations. Okay. So when you're coding it, you basically code your O out is equal to so and so, and then your B out are like zeros for everything. Okay. So the whole thing is zero, and then similarly the whole thing is zero. Okay. So what does set less than do? What happens? What do you think this operation will do? You know, you have O output, right? Which is, so if you see your description, it says like A less than B. Okay, signed or unsigned. So what is the output? What should the output look like? What are the 32 bits? Okay, so do you guys know logical operators of VHDL? Yeah?
So
They are greater than, less than, equal to, sorry, these are relation operations. Okay, and then greater than, equal to. Do you guys remember this?
So it's like a true or false.
Yes, so the output is Boolean. Okay, so Boolean is how many bits? 1 bit, right? So, however, O out is 32 bits. Correct? Can you represent Boolean in O out? How would you do it? You're right, but yeah.
1 down to 0.
Okay, so you would represent, so you need to represent all 32 bits, okay? So all zeros is your 0, and then 0, 0, 0, 0, all the way 1, just 1, that's all, okay? So ideally Boolean is just 0 or 1, okay? But since you have 32 bits, you just represent the whole thing in 32 bits, that's all. Represent 0 in 32 bits and represent 1 in 32 bits, that's all, okay? So say for example, if you ask like set less than and give A and B, your output should be all zeros or like all zeros or 1. So that should be the output when you verify these operations, okay?
Why is there two functions for the add and subtract? Is that signed and unsigned?
No, it's not signed and unsigned. It's complete. It's the same thing actually. So it's the MIPS functionality. So the MIPS has like two functionalities. Okay.
They call the same thing.
Yeah, to call the same thing. So it's like the thing is, MIPS has some other functionalities also. So it can use these instructions inside it. If you go through, the appendix B of the textbook, you'll understand like based on other functionalities, these values will change. Okay, so for this project, you can assume both as addition, both as subtraction. Okay. Similarly, okay, so based on these branch instructions, your branch outputs will change. Okay, so if there is a branch, then branch will be 1. If there is a jump, then jump will be 1. Okay. However, the output is always A here. A is basically your source register. This is your RS. This is your RS. This is your RT. Okay. So the thing is over here. So when you are coding your ALU, in your case statement, you should have this also. Okay. Although you are not verifying it, you should have this. Okay. If opcode, if functionality is like 111000, then output is equal to A, and then branch out is equal to you have to verify it. If A equal to B, then this is 0, 1, or else 0, and then jump is 0. Okay, so you should have case and if statements in your ALU. Got it? Does it make sense? Yeah. Okay. All right. Is ALU clear? You guys need me to explain anything else in ALU? No? Good, okay. Can I erase this? Yes? Is ALU a sequential block or a combination block? Yeah? Somebody said something. Go ahead, don't be scared. Yeah, ALU is a combination block. There's no clocks and resets, so it's a combination block. You're right. Okay, so we are done with program counter, instruction memory, register file, ALU, and data memory. Okay, data memory is basically the same thing as instruction memory, whereas over here you have like address in, data in, and then data out. That's all. Okay, so it's basically the same thing.
Is there a clock on that?
There is no clock here. Hold on. No, actually it has a clock. It doesn't have reset, but it has a clock. Can you check the entity of the data memory?
Yes.
It has a clock, right? It doesn't have reset though, okay? So over here, this is write enable for your data memory, okay? If write enable is high, then it's writing. If write enable is 0, then it's reading, okay? You need to keep that in mind. All right, okay. So next is the controller, okay? So in your, I don't know how you guys did in your 31L, so maybe different people did it different way. So in 31L, I remember few people, what they did was they used to take the complete instruction, the controller, and then in the controller they used to like separate everything, right? I don't know if you guys did. Do you guys do that? Do that way?
I think so.
Yeah. Okay, some people did that. So what people did was like, take 32 bits of 31 down to 0 to your controller. and then your RS, RT, RD and stuff, and then this goes into your register files and stuff like that, okay? Whereas here, you're not doing that. You're generating only the control signals for all these blocks. You're not generating your values, addresses over here, okay? So addresses you're writing in your main code. When you write, so these are all the individual blocks, so you need to write one more big code like processor block in which you do all the connections, right? Right? So in the processor block you make these connections, okay? What controller does is only these bits, the opcode and the functionality, okay? So 31 to 26 is the opcode, right? Right? The first 6 bits and the last 6 bits. The opcode and the functionality goes to the controller, and based on these things, your controller will decide what it is. Is it load register? Is it based on your opcode and functionality? The controller will decide, okay, if it's a load instruction or a store instruction, or is it addition or subtraction. Based on that, it gives you correct, outputs. Okay. Over here, the controller is one of the hardest block to code. Okay. Earlier in 31L, controller was super easy, whereas here controller is probably the hardest block over here. Okay, so you need to keep in mind all the instructions. For now, I think you can avoid the branch instructions for the controller. Okay, but you'll probably have to add all the branch instructions later. Okay, so you just probably have to make modifications to the controller. But for now, you can avoid the branch instructions. Okay, so the main thing you need to understand is opcode of load word, store word, okay? So you need to, first thing you need to check for the opcode. If the opcode is 35 or something, then you need to figure out what controls to give and then what controls not to give, okay? So, are you guys familiar with the control path? Okay, so this is basically data path, okay? So the control part is another concept. So basically what happens here and here. Are you guys familiar with the control path? Yeah? Okay, so let me give you a brief example of the control path, okay? Okay, cool. So let's have an instruction. Let's take an example, okay? So let's have add.
Like that.
Add dollar
Terminal tab. You just navigate to where, let's say it's where am I?
Okay, so this is my instruction. Alright? So first thing you need to remember is what type it is. Is it R type or I type? R type. Okay? That's the first thing to remember. Okay? And then first things first, okay? So when I give that instruction, right? So my okay, actually let's have the 32-bit values. So opcode is 0000000, right? RS is say this is RT, RS, RD. Is it right? RS, RT, RD? Or is it the other way?
The source is
This one?
the source RS. No, the RS.
No, I'm talking about the MIPS.
Oh
Assembly
yeah,
language.
so the destination's on the left.
Yeah.
I thought you meant
RS, RT?
Yeah, I think that's what it is. RT1.
I think it's RS or
Okay. Okay, fine. Okay, let's have this for now. Okay. So RS is 3, so 0, 0, 0. 3 is
Yeah, everything should be changed inside these files. It's already done.
okay. RT is 0, 0, 0. RD is 0, 0. Add is 1, 2, 3. Okay. So this is 31 to 26, 25 to 21. This is 20 to 16, 15 to 11, 10. Okay? Does it make sense? Does the instruction set make sense? Okay. Alright, so this is my instruction which is coming from the instruction memory. Okay? So what will happen here? So my opcode is 0, 0, 0. Function is 1, 0, 0, 0, 0, 0. Correct? Yeah? So my RS is 0, 0, 0 and then 1, 1. Okay? RT is 0, 4, 0, 0, 1, 0, 0. This is 0. Okay. All right. So first things first. So initially, what are the control states? So what are the controls here? Register. So forget branch. You have register destination, and then memory to register, memory write, ALU control, ALU source, and then reg write. Okay. So first thing is what should be the register destination here? This should be 0 or 1. One? That's correct. Yes. Why would it be 1?
Because it's going to be writing the result.
That's correct. So this would be 1. Okay, does that make sense? So it has to write back. So it's basically checking what to write. Okay, either RT or RD. So RD, write address should be RD, destination address. So if the mux is 1, then this is the input. Okay, so basically this is my path of the data. Okay. And then this goes here, and then this goes here. Okay. Next, what will happen here? So next controller is basically this controller. So what is this controller? What should this value be?
1.
1? Correct. So this would be 1. Why?
It's not right.
It has to write. Correct. The same concept. Okay. Next is this mux. Correct. So what is ALU source? What it should be? What should be the value of ALU source?
0.
0? Correct. So it has to select this output. It should not select the immediate value, right?
Yeah.
It should select the value from the register. So this should be 0. Okay? So this read data 2 will come here. So this is the path. So this is the path, and then this is the path. Okay? So the next thing is ALU will get the both values, and what should be the ALU control here?
The function.
The function. So this function, this value directly should go to the control. Correct? Function is 1, 0, 0, 0, 0. 0. Okay. So next my output will come here. Correct? So what will happen? What is the output? What is these two bits? My memory write and memory to reach. Zero? Why?
Because you're not storing.
You're not storing. That's correct. That makes sense? Does it make sense? Yeah? You're not storing any value here, right? So this is 0. You're not writing anything. Okay? So what is this?
What is this cadence? Yeah, what's
That's 1.
1? Correct? So this is selected. The output is selected. So this is my data path. So it goes here, and then it comes here,
I don't know how cadence works.
data path, and then
Yeah,
since write enable is high, and then instruction is so, this value will be written here.
I think you should process it.
Okay? This is my data path for R-type addressing. Okay? It completely ignores the data memory. Okay? Is this clear? Okay? So you know what values to give here based on your instructions. Okay? You need to make sure you need to give like these inputs for all ALU instructions. Okay? For addition, subtraction, all logical operations, branch instructions. You can avoid, I think you can avoid branch instructions for now, but yeah, I think you can avoid branch instructions for this assignment, okay? So for everything else, you need to make sure you need to give this. So for this assignment, you should be able to execute add, subtraction, so add, sub, and or XOR, NOR, and load word and so okay? Okay, so you need to do all these instructions. You should be able to do all these instructions, okay? Okay, so R-type instruction is clear, correct? So let's do an I-type instruction, okay? So can you give me an example? Is load word I-type instruction? Yes? Okay, so let's do an I-type instruction over here. So load word $0, $1, maybe 0001, 16. Okay, it's a hexadecimal value, okay? Or just 1 basically. Yeah.
You can't load it as $0, can you? Because the 0 is always 0. 0 is always a 0 value.
Is 0 always a 0 value?
Yeah, that's your constant. That's your
Oh
constant
yeah,
0
okay,
value.
okay, sorry. Okay, fine. Two? Does that make sense? Okay. Yeah. So what will happen here? So okay, so what's the opcode here? For load instruction? It's 35 decimals, so it is 100011. Okay, so RS RT, is it right? Or is it the other way around?
I'm not sure.
Okay, just assume this first now, okay? So RS is 2, so 00010. RT is 0.00001. Okay, and then there is a decimal value. Okay, so 16 bits. Okay, so this is my instruction. Okay, so let's follow the data flow. Okay. Here is this.
Yeah.
Okay, cool. Alright, so here, what happens to the opcode? So instruction is 100.011. Okay? So is there any functionality?
No.
No. Okay, so however, this value will obviously go here, so this will be 00001. Okay? So you should be able to ignore that functionality, okay? Automatically. Sorry?
For I-type.
Yeah, for I-type, yeah. So you should look for op-select and then like you should check for opcode initially and then you should be able to avoid the functionality, okay? Okay, so this will be 00 010. Sorry. 00010 and then this would be 00001. Okay? So what would be the value of this mux? 0? Yes. Why 0?
Because you don't want to pull in part of the.
Yeah, correct. And then even if you write, you need to write into this value. RT value, not RD value. There's no RD there. Okay? So that's why it is 0. Okay? So this bit is 0. Okay? So the next thing is, what is this value? So what is reg write? 0? Are you sure?
I don't know, because you're still gonna write.
You're still gonna write, right? Yeah, so this should be 1. Okay? So you still need to go right back into my RT. So this should still write. Okay, it should be 1. So what is the value of this mux? 1. Because you need to write the sign extended value, right? So this will be 1. Okay? And then what is the functionality here? What happens? So, can you tell me what happens here? Value of $2 plus 0.00001
So to add 0. Oh,
comes to $1. Sorry. Yep, sorry, yeah. Comes to value of $1, right? So basically adding for load instructions. Right? So if there is a load instruction, your ALU control should be add operation. Does that make sense? So now, okay, so this is the output. So what happens to memory, what happens to this value and what happens to this value?
0.
Is it 0?
Yeah.
Are you sure?
Yeah, I'm saying.
Yeah, because you're reading, it's not writing, right? You're reading from memory.
No, wait a minute. So you're reading from what memory?
Data memory, right?
Yes. So this is the address, right? So basically what happens is
So you want write enabled.
this is the value of this is the address of data memory. Okay, so the data of this basically goes to here. Okay, so you need to access the data from the data memory. So address is given from the ALU. Okay, so you need to
But write enabled should be 0, right?
write enable should be 0. Yeah, that's correct. Okay, how about this one?
0.
0, because you're selecting this value. Correct. So if we come back, the path. Okay, so this is correct. This is the data flow, data path. Okay, and then it goes to the data memory, and then it comes back, and then writes into the register. Okay, so this is for I-type instruction. Does that make sense? So you guys need to figure out for all the operations, for load and save. Okay, so the textbook is like really good resource for you to figure out. So if you are like super confused, I think section 4.4 in the textbook will give you a good way to design the controller. Okay, yeah.
Is it the entire like flow of the data? Is it word addressable or byte addressable? Because MIPS is byte addressable.
You can have this as word addressable.
As
Yeah, it basically it's how you design the memory. Okay.
I think you said to do it by addressable.
byte addressable?
Yeah.
The teacher, I think.
Yeah, I think it's a byte addressable, but like ideally you can design. So basically the addressable is basically for your memories. Okay. So if you because the size of the data memory is 32. Okay, it's like 4 bytes. Okay, if you do it a word addressable, then you should have like 8 words. But you can, if it's byte addressable, then you can have 4 bytes. Okay, so it really, in that case, if you're using byte addressable, what you can do is you can add 4 here instead of 1.
Yeah.
Okay, so yeah, if you're doing word addressable, then you have to add 8. That's all. Okay.
Also, is this like good enough for the PDF for the assignment 1? Do I have to put anything under what you run? Yeah, like this is a pretty easy software to use. I put a description.
Yeah,
And then I
that
can
should
get
be
it,
good
and then
enough,
the waveform. Yeah, put it automatically. What about what you've learned?
I mean, you can write whatever you want, so you can say like.
I do write something.
Yeah, you have to write
Okay.
something. Yeah.
Okay.
It's your report. You can write like whatever. A couple of like probably 4 lines, 2 to 3 lines is good.
I don't know what to say for quest system description. I just said it's a tool set okay on Linux. I followed the tutorial and I had no issues. I included the
That's good enough,
optimized
yeah.
simulation line.
So the main objective is for you to learn Linux. Okay, so sorry, latex. So it really doesn't matter what you write there. So it's like as long as you write something in latex. Okay, so don't worry about it.
It's not that hard. There's all this stuff in like the beginning with like HDL,
Yeah.
more keywords. We don't even use it, right?
No, not
For this
really.
project.
Yeah. Okay. I think next week is holiday, right? President's Day.
Yeah.
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 Yeah. So there won't be any lab, but like if you want to like come, you can like come to other lab sessions. Okay. So
So
maybe.
our lab session is not like available, but like the other ones will be still.
Mhm.
The other labs will still be available.
Yeah, it's still available. If you want, you can
So
come
it's
to
just
those
that
labs.
day.
Okay. Yeah, and then.
And then we have another one. There's 2 Mondays.
Yeah,
every
the 2
day.
Mondays.
Yeah, it's
yeah.
too much.
So the thing is, by the end of this week, we'll give you a small test bench, and then like the whole thing should work in the test bench. Okay. So later you have to design another test bench and then make sure that that works too. Okay. So you don't need to worry about the test bench right now. So try and
You
design
said
the
you'll
whole.
teach us next week.
Sorry.
Said, the professor said we'll learn it next week.
Yeah. Sure.
And
Okay.
Make a
Mhm.
system umbrella.
Yeah. Okay. Sure. And then yeah. This week you've been basically concentrated on writing the whole thing. So once you do this, then it should be super easy.
Okay. And then how do I cancel a ticket from OIT?
I'm really not sure.
Because I went on the website and I click it, but there's no action for me to cancel. I think they have to do it.
Yeah, I mean, I think there's a comment section over there. You can comment, you can write.
Yeah, I
description.
comment said ignore this.
Yeah, that should be good enough. They'll take a look. Yeah, yeah.
One day they'll get to it, maybe like 3 weeks from now.
I don't know. Yeah, maybe depends on people working
Yeah,
there.
you're just saying it doesn't matter now.
Yeah, it depends on people working there. I'm not sure. I have no clue who's working, so I don't know.
That's you just telling us assigned it.
Yeah, then yeah, you can just let it be. Since you've done your work, that's good enough. Yeah.
So for the log files, how do we get them from, like, how do we like SCP from remote to the local?
If you go to the class website, there's a tutorial, SSH tutorial. Just down the tutorial, and then like all the way down the tutorial, there's like a command to show you how to transfer files. So you can use those commands in the
Because I
class.
was able to get from local to remote. but-
So it's the same. It's the other way. So it's the same thing.
So it's in that, it's also in that tutorial.
Yeah. Okay. Or if you don't want to do that, then you can download CyberDuck. CyberDuck, you can just drag and drop copy files.
Even for Unix based.
Yeah, for Mac. CyberDuck is for Mac.
For this
Yeah.
assignment, we can use
You don't use
ISC,
files on
Xilinx.
Go ahead. Yeah. You can use whatever you want. Yeah.
Which is faster, Xilinx or Quest system?
Both are equally fast, actually.
Because Sim died on me for my last project week. I exceeded at 10,000 lines or something. Like
Yeah.
too many generates.
In that case, QuestaSim is better. The license, there are like industry licenses are available for QuestaSim. So it's like you can write, 1 million line code and it'll still work.
Yeah,
Okay.
Sim wrote how to use Xilinx.
Yeah, in that case, Xilinx also will work. So it's completely up to you. It's, you decide whatever is convenient for you. You can use whatever code you want. Yeah.
What do you need to package? What do you want to see inside the zip file?
It's on the thing.
The zip file, you need all the files. You need like your PDF, your .tex file, and all the files. Your PNG, JPEGs, and everything. All the additional files.
So do we need the logs then, or?
Yeah, I mean, like the logs will be like in a PNG format or JPEG format, right?
Well, those are the waveforms, right?
So okay, you can take the screenshot of the logs if you want, but if you're just putting the logs, then put the files directly there and then zip the whole thing.
Yeah, I have the files with the .log extension.
It's also fine. You just put the whole thing and then
They'll
zip
be
it.
able to
Okay.
read it, right?
Yeah, the grader should be able to read it. Yeah, the easier way would be to take a screenshot of the log file, but that's also good enough.
Yeah, that's what.
Well, you can also put
Yeah,
like
that's what the grader recommended. So yeah, the grader wants the screenshots, but if you have log files, it's gonna be like hard on the grader, but I think the grader should be fine.
Oh, then I'll just take screenshots.
Yeah, because he wanted you to screenshot and by like
Mhm.
elaborate, compile, and simulate.
Yeah.
I'll have the logs for build, elaborate.
Yeah, I mean, you guys should look up the discussions on the class website. The class website discussions have all these answered. all these questions answered. Okay, so take a look at the discussions once in a while so that you'll know. Yeah.
I don't think so. Oh, is it deliverable?
Do I need to zip up the cadence files we used, and that's quite soon.
Sorry?
Do we need to zip up these files too?
And it's only one.
Yeah, zip
So
everything.
it's for one person,
Yeah,
right?
zip everything.
Not in a group.
Yeah. This individual report.
Yeah.
Project 1.
Oh, even the VHD,
Yeah,
that's the same.
Yeah, it's the same for everyone,
Yeah.
but like
All these are shared like
The only thing that's, I mean, even the
just the
waveform,
report and waveforms. Okay,
it's
you
just the
can
waveform
And the
might
log, right?
become
Yeah.
different. 'Cause
So I
it's
don't know what that is.
you don't need it, but yeah. But if you want to put it. It's okay. It's not a big deal.
Like the what do we do like
I don't like the latex one.
and not like the CGS.lib or like whatever.
You don't need them. Yeah.
Okay, these
What are they? I don't know these ones.
report that one.
Oh, those
What do you think?
Oh. Nah, I'm not.
It's a bit lengthy as a thing, so
Mine's fine.
if you know the basics of the process, you
Sorry.
Well, it's because you didn't get it finished in PDF. That was good.
Yes.
Yeah, that's fine. It's whatever.
I don't want to SSH.
Oh wait, oh I already have a log.
That makes sense. Your situation is.
And then cadence refuses to work. I'm pretty sure I just deleted my account on some servers. Like, I ain't gonna do it. 'Cause I never really used it after it used anyone else. I don't